All right, so we're going to continue on this video, first talking about the fundamental theorem of algebra. The fundamental theorem of algebra says a polynomial function of degree n, where n is greater than 0, has at least one zero, real or imaginary, in the complex number system. So now we're going to have zeros that are imaginary. So for every imaginary zero that we have, according to the conjugate root theorem, if we have a complex zero of a plus bi, then we're actually going to have its complex conjugate, a minus bi, also as a root. So for every imaginary number, we're also going to have its conjugate. So looking at this first example, it says write a polynomial function of least degree with real coefficients in standard form that has -2, 4, and 3 minus I as zeros. When we take a look, we know using our factor theorem that this -2 is actually a factor x plus 2. That this 4 is actually a factor x minus 4. I'm going to use that same knowledge and apply this zero of 3 minus I. So x minus the quantity 3 minus I. And we also know, because with every complex number, we're also going to have its conjugate. So x minus the quantity 3 plus I. So now we need to expand each of these out. First things first, I'm just going to simplify this a little more so we can have fewer sign errors. This becomes x minus 3 plus I. This becomes x minus 3 minus I. So let's go ahead and distribute these two binomials first. When we do, we get x squared minus 2x minus 8. Now, we need to distribute these polynomials. So x times x gets us x squared, so plus x squared. X times -3 gets us -3x. X times -I gets us -xi. All right, and then we have -3 times x gets us -3x. Oops. -3 times -3 gets us that +9. -3 times -I gets us +3i. All right, so now we have to do I times x, which is ix, or my apologies, xi, real part before imaginary. I times -3 is -3i. And I times -I is -I squared. All right, now we have a lot of terms here, so let's take our time and really be cautious about simplifying these out. Except for the fact my sugar made a horrible mistake. There we go. We're not adding these, we're still multiplying. Whew. There we go. All right, let's go ahead and simplify what is inside our second set of parentheses before we try distributing it to our trinomial in front. All right, so let's take a look. We have x squared, no more x squared, so I'll put this down as an x squared. And I'll scribble this one out. All right, we have a -3x and a -3x, so that gives us -6x. So I'll scribble those out. All right, we have xi, -xi plus xi. Those actually cancel. Not bad. We have a plus 9. So I'll scribble that out. I have a positive 3i and a minus 3i. Those cancel. And I have a minus I squared, which is minus negative 1, which we know equals 10. So I have x squared minus 2x minus 8 times x squared minus 6x plus 10. All right, so now I have a trinomial times a trinomial. We want to make sure and distribute each term in this first trinomial to each term in the second trinomial. So let's start with green. So x squared times x squared is x to the 4th. X squared times negative 6x is negative 6x cubed. X squared times 10 is 10x squared. All right, so that was this first term by everything in the second set of parentheses. So let's do the second term by everything inside the parentheses. So we have negative 2x times x squared is negative 2x cubed. Oh, negative times a negative is negative 2x times x squared is negative 2x cubed. Whew, I'm getting ahead of myself. Negative 2x times negative 6x is positive 12x squared. Negative 2x times positive 10 is negative 20x. And then that last one, we have negative 8 times x squared is negative 8x squared. Negative 8 times negative 6x is positive 48x. And then negative 8 times positive 10 is negative 80. All right, let's keep simplifying this down. The x to the 4th doesn't have any like terms, so we'll pull it down. I'll go ahead and mark it out so I know that I've worked with it. Then we have negative 6x cubed minus 2x cubed, which gives us negative 8x cubed, so negative 8x cubed. I'll mark those out. We have positive 10x squared plus 12x squared, which is 22x squared, minus 8x squared gets us 14x squared. So I'll mark all those out. I have negative 20x plus 48x, which gets me positive 28x. And then the minus 80 is all by itself, chilling out at the end. All right, that is how we write that polynomial function. It used a lot of that distributive property, a lot. And so make sure you're taking your time to write out each one of those steps. All right, going on. So a function has complex zeros when it is factored form contains a quadratic factor which is irreducible over the reals. A quadratic function is considered irreducible over reals when it has a real coefficient but no real zeros associated with it. So when that happens, you'll see that every polynomial function of degree n greater than 0 with real coefficients can be written as a product of linear factors. That's a key here, a product of linear factors and irreducible quadratic factors, each with real coefficients. So let's go ahead and work an example from beginning to end. It says, example, k of x equals x to the 5th minus 18x cubed plus 30x squared minus 19x plus 30. So part A says write k of x as a product of linear and irreducible quadratic factors. Part A is the big part. So first things first, let's identify our p, which equals 30. Let's identify our q, which equals 1 because our leading coefficient is 1. Now we need the factors of 30, so plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 5, plus or minus 6, plus or minus 10, plus or minus 15, plus or minus 30. The factors of Q are plus or minus 1. So when we have our P over Q, we have quite a lot of factors to look at. We have 1 over 1, so plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 5, plus or minus 6, plus or minus 10, plus or minus 15, then plus or minus 30. So right there we have 2, 4, 6, 8, 10, 12, 14, 16 possible rational real zeros that we could use with our substitution. However, if you recall from earlier in the past video, there is a test that we can use to help narrow that down. And so we're going to look at our upper and lower bounds. So first things first, we're going to enter this into our graphing calculator. Whether you have one in your hand or if you have to go to Desmos, you're going to have to enter this polynomial function into the calculator. All right, so here we've graphed our function in the Desmos calculator. And if you notice, we have it crossing 3 times, and we're going to look at the intervals at which it's crossing. It looks like it's crossing at -5. We don't know that for a fact yet, so we're going to push our interval 1 to the left. So we're going to go from -6 all the way to, let's say, +4. So when we go back, we'll say, hey, based on our upper lower bounds test, we're only going to look at values from -6 to +4. So that includes +1 and -1, +2, -2, +3, -3, but it gets rid of +5. It gets rid of +6 and gets rid of altogether +10, +15, and +30. So we went from 2, 4, 6, 8, 10, 12, 14, 16 zeros to 2, 4, 6, 8. We literally cut the number of zeros that we are going to have to test in half. So now let's talk about that remainder theorem. Let's see if we have any remainders. We're going to substitute each of these values in to our function k of x. If it equals 0, that means it is a factor. If it does not equal 0, that means there is a remainder. So let's take a look. The first one we have is k of +1. And at this point, you guys are in pre-cal, so I would expect you to know how to evaluate a polynomial function. So k of 1 equals 24, so not a factor. K of -1 equals 96, so once again, not a factor. K of 2 equals 0. All right, so that tells me, hey, that 2 is going to be a factor. Next, we'll go to k of -2. That's 300, so not a factor. We'll go to k of 3, which equals 0. So once again, we do have another factor. Then we'll do k of -3, which equals 600. We'll go k of -5, which equals 0. So once again, here's another factor. And then we have k of -6, which equals -2, 2, 6, 4. So not a factor. So here we have 3 possible rational zeros that we used using that remainder and factor theorem. So now I'm going to take that information and I'm going to do my synthetic substitution. So let's start with 2. 2, and then we had x to the 5th, so 1x to the 5th. We had 0x squared minus 18 plus 30x squared, so we'll put a 30, minus 19x plus 30. So when we use the synthetic substitution, this last column should yield a 0. So we'll bring down our 1. 2 times 1 is 2. 0 plus 2 is 2. 2 times 2 is 4. Negative 18 plus 4 is negative 14. 2 times negative 14 is negative 28. 30 plus negative 28 is 2. 2 times 2 is 4. Negative 19 plus 4 is negative 15. 2 times negative 15 is negative 30. So we have a 0. Perfect. So now, what that actually represents is 1x to the 4th plus 2x cubed minus 14x squared plus 2x minus 15. So that is our current polynomial. It's almost fully factored, but not quite. So now we're going to take our next 0 of 3 and use that synthetic substitution on this new polynomial. So we have 1, 2, negative 14, 2, negative 15. All right, bring down the 1. So 3 times 1 is 3. 2 plus 3 is 5. 3 times 5 is 15. Negative 14 plus 15 is 1. 3 times 1 is 3. 2 plus 3 is 5. 3 times 5 is 15. So once again, it works, 0. So now we have x minus 2 from above. Now x minus 3. And now this is x cubed plus 5x squared plus x plus 5. All right, still not fully factored. So we're going to continue on with our next 0, which was negative 5. So negative 5. And so we have 1, 5, 1, 5. When we bring this down, we end up getting x minus 2 from above, x minus 3 from above, and now x squared plus 1 from above. All right, so this is our fully factored. This is our product of this is our product of linear and irreducible factors. So that's part A. Here's our linear factor, here's our linear factor, here's our irreducible factor, because this is x squared plus 1. It cannot factor any further because it is a sum of perfect squares. So now we have to go to part B. Part B. So part B says, hey, write the product of these linear factors. Well, we know we have a factor of x minus 2. We know we have a factor of x minus 3. We know we have a factor of x minus 5, which apparently I forgot to write down here. So let's go back and write that. X minus 5, x squared plus 1. That's a lot better, Mrs. Younger. And then we have x squared plus 1. So now we really want to break this down even further. So we're going to set this equal to 0. So we can get its actual factors. So x squared equals negative 1. X equals plus or minus negative 1, which we know is x equals plus or minus I. So now the fully factored product of linear factors is going to be x minus 2, x minus 3, x minus 5, x plus I, x minus I. And there's part B. Part C says, okay, now you have your fully linear factors, you have the product listed above, give me my zeros. So your zeros are x equals positive 2, x equals positive 3, x equals positive 5, x equals negative I, and x equals positive I. And how did we find those again? We set each of these pieces equal to 0. All right. So yeah, we just worked an example from beginning to end. We're actually going to do that one more time. But this time we're actually going to look at something a little bit more complicated with that synthetic substitution. Up until this point, we've only been using real numbers when doing our synthetic division. But now we're going to use complex numbers. So I'm going to work out an example with you with the complex numbers. So make sure you have plenty of room to write this all down. It is a doozy. So it says find all the complex zeros. P of x equals x to the fourth minus 6x cubed plus 20x squared minus 22x minus 13, given that 2 minus 3i is a zero of p. All right, then write the linear factorization. So we have 2, oops, let's get a pen that isn't a highlighter. So we have 2 minus 3i. That is the factor we're going to use in our synthetic substitution. We have a coefficient of 1. We have a coefficient of negative 6. We have a coefficient of 20, of negative 22, and a constant of negative 13. We're going to go through this the same exact way we would normally. We drop down our 1. 1 times 2 minus 3i is 2 minus 3i. So now, negative 6 plus 2 minus 3i is negative 4 minus 3i. All right, so now I have to multiply 2 minus 3i times negative 4 minus 3i. I'm going to go over here, and we're going to show how that works. So 2 minus 3i times negative 4 minus 3i. I have a binomial term times a binomial term. So 2 times negative 4 is negative 8. 2 times negative 3i is negative 6i. Negative 3i times negative 4 is positive 12i. Negative 3i times negative 3i is positive 9i squared. So 9i squared. All right, so now let's keep simplifying this out. We have negative 8 plus 6i plus 9 times negative 1. So now we have negative 17 plus 6i. That is what yields when we multiply this by this. So I'm going to put negative 17 plus 6i. And I'm going to add straight up and down like I normally would. 20 plus negative 17 plus 6i gets us 3 plus 6i. All right, I have to go and do that binomial times binomial again. So this time I have 2 minus 3i times 3 plus 6i. So 2 times 3, we get 6. 2 times 6i, we get plus 12i. Negative 3i times 3, we get negative 9i. Negative 3i times 6i, we get negative 18i squared. So now we have 6 plus 3i minus 18 times negative 1. So we get 24 plus 3i. So I'll put 24 plus 3i here. All right, so when we add this up and down, we get 2 plus 3i. All right, so we have to go through and we have to show 2 minus 3i, 2 plus 3i. Because these are complex conjugates, here's a reminder, you only have to multiply the first times the first, which in this case is 4, and the last times the last, which is negative 9i squared, which gets us 4 plus 9, which is 13. So here we get 13, and yes, in fact, it did yield us a 0. So now, we know that 2 minus 3i was a 0. However, according to the conjugate root theorem, I also know that 2 plus 3i is a 0. So I'm going to bring down my new coefficients, and I'm going to do synthetic substitution all over again. All right, the 1 comes down. 2 plus 3i times 1 is 2 plus 3i. All right, so now negative 4 minus 3i plus 2 plus 3i is really nice. It equals negative 2. How did we get so lucky? So now I multiply 2 plus 3i times negative 2, and that gets me negative 4 minus 6i. Ooh, look at it again. I'm left with negative 1. 2 plus 3i times negative 1 is negative 2 minus 3i, and I'm yielding that 0 again. So now, of my factored forms, I have 2 minus 3i, 2 plus 3i, and x squared minus 2x minus 1. All right, here's the thing. Can this be factored? It cannot be factored. So we're going to use the quadratic formula. If you recall, the quadratic formula says x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So in this case, a equals 1, b equals negative 2, and c equals negative 1. So you get x equals negative b, which is positive 2, plus or minus b squared, which is 2 squared minus 4 times 1 times negative 1 all over 2 times 1. So x equals 2 plus the square root of 8 over 2. So x equals 2 plus the square root of 2 over 2. We can simplify this out. X equals 1 plus or minus the square root of 2. Which we know, because of the plus or minus, we have 1 plus the square root of 2. We have 1 minus the square root of 2. So, our linear factorization says that we had 2 minus 3i as a factor, 2 plus 3i as a factor, and then x minus the quantity 1 plus square root of 2, and x minus the quantity 1 plus the square root of 2. There is our linear factorization. That solves the problem. I answered the question. This video is done. If you have questions, please feel free. Ask me in class, message me on Teams, send me an email. Just reach out to me. I would love to help you out. I hope you have a fabulous day.